proposed was the evidence of paleoclimatic data that lined up. So after there was enough evidence for a glacial period dating to the Paleozoic era in South America, in Southern Africa, Australia, and India, his suspicion for a paleoclimate was in fact asserted. So what this means is that about 300 million years ago, a large sheet or ice sheet covered extensive portions of the southern hemisphere as well as India. All of these areas that the large ice sheet covered are now lying about 30 degrees from the equator in a tropical or subtropical climate. So one of the proposals suggested that in fact that the whole planet underwent a period of extreme cooling, but Wegener rejected this proposal by saying that during this time span, the northern hemisphere actually had swamp remains, remains that got buried and that are now one of the sources of coal in our planet, for example. But for these were made mostly from ferns with large fronds to form in the first place, they must have been under warm and moist conditions, like the tropical or subtropical climates. So what he thought was that having the southern land masses be covered by some sort of ice sheet, and at the same time having the current northern land masses to have swamps at the same time period, this meant that all of the land masses probably were much closer to the South Pole than initially thought, rather than an extreme cooling of the planet, again because of the swamps. And that also correlates with the Glossopteris fossil remains that were found later on in their specific nature, that they could only form in cold weather climates. All right, so again, based on the three lines of evidence that we looked at, so this one about the paleoclimate, the previous one about the rocks matching, and then the third one being the fossil correlation, as compelling as that evidence may have been, about 50 years passed before most of the scientific community really accepted the concept of continental drift. And partly because it was so new, right? It was so innovative. And most of this evidence, again, came from findings in the southern hemisphere. But this skepticism also had to do with some of Wegener's explanations for the physical forces that caused the movement of the land masses. And that's what we'll cover in the next slide or two. So from about 1924, which is when Wegener's book was translated into English, French, Spanish, and Russian, and until Wegener's death, which was in 1930, for those 6 years, the continental drift hypothesis was highly criticized. One of the main reasons for this criticism was that Wegener's hypothesis lacked a credible mechanism for the continental drift. He proposed that it was gravitational forces of the moon and the sun, which are what currently produces the Earth's tides, that were in fact capable of gradually moving the continents across the globe. So this idea was argued by Harold Jeffrey amongst others. Harold Jeffrey was a physicist who said that if indeed these tidal forces were of that magnitude to move the continents, they would have actually resulted in halting our planet's rotation if they were that big. And as we know, this halting of our planet's rotation hasn't happened. So he refused this idea for the mechanism of movement. Also, Wegener thought the stronger and the sturdier continents that traveled through the globe, they did so by splitting and breaking the thinner oceanic crust areas, such as icebreakers cutting through ice. And now we know that this was also incorrect, given the densities of both types of crust. But back then, it was argued against because of the lack of deformation of the continents. So, if you think about the continents that were the sturdier land masses traveling through this weaker oceanic landmass, being the ice-like idea in the analogy, then the continents would have received a lot of deformation in the specific place where they were cutting through this oceanic crust. So all the rocks in that edge or in those edges would receive a lot of deformation, a lot of change, and that we have not seen in a specific edge of the continent necessarily. So that's why this idea was argued against back then. Now we know the different densities of the two types of crust, so now we can argue against it that way. So Wegener died on his fourth and last trip to Greenland in 1930, but his idea of continental drift did not die, which is great. And although the idea had some flaws in respect to the mechanisms for continental drift, as we just saw, in that, yes, not all of the evidence supported the hypothesis, its central theme about continents drifting throughout the planet and about Pangea, basically, it was correct and was a good basis for the theory that was later proposed, which was the theory of plate tectonics, which we'll cover in the next few slides. So there were a few discoveries made after World War II that helped reawaken the continental drift hypothesis, and that gave better idea for the mechanisms of continental movement. It was after World War II that there was a lot of oceanographic exploration thanks to the new equipment and marine tools that had been developed, as well as large amounts of funding from the U.S. U.S. Office of Naval Research. So this amount of exploration led to a mapping of the seafloor, where many features could now be seen, such as the global oceanic ridge system that winds through all of the major oceans. This ridge system is what we call now the mid-ocean ridge. Another discovery made in the Western Pacific demonstrated that earthquakes happen at great depths in oceanic trenches. Another important finding was that after dredging of the seafloor, the ages found were all of crust younger than 180 million years old. So nothing older than 100 million years old could be found in the oceanic crust. On top of all these things, it was also found that the sediment accumulations in deep ocean basins was fairly thin, not the thousands of meters that they initially predicted that they were going to be. They were fairly thin. So that also kind of contributed to the idea that the crust was young, because if it had been old, a lot more sediment accumulation could have been emplaced. If it was younger, only so much sediment could have actually been deposited. So, thanks to all of these discoveries, among others, this led to an unfolding of a far more encompassing theory than the hypothesis of continental drift. This theory that came about is known as the theory of plate tectonics. According to the theory of plate tectonics, the crust and the uppermost mantle, which is also the coolest one, are Earth's strong outer layer, which we call the lithosphere, as we saw in the last chapter. When there is movement within the lithosphere, it causes bending or breaking within it, because it's cool and it's strong in nature. So this lithosphere varies in thickness and in density depending on whether it is oceanic or continental lithosphere. When it's continental, it tends to be less dense and thicker, and when it is oceanic lithosphere, it tends to be denser and thinner. So the oceanic lithosphere is about 100 kilometers thick in ocean basins, but it's considerably thinner near ocean ridges. Okay, this is important, and it's something that we'll touch on later in the chapter. Continental lithosphere, as a contrast, averages about 150 kilometers in thickness, but in certain places it may extend up to depths of 200 kilometers or more. And again, this would be in areas where there's stable interiors of the continents. So oceanic crust is also denser than continental crust, as it is composed of basalt, a rock type that is rich in iron and in magnesium. Both of these elements are dense elements. Continental crust, in contrast, is composed largely of mostly granitic rocks, which tend to be lighter in terms of density. So due to these crust differences that I talked about, the density differences, it makes the oceanic crust, or lithosphere, overall denser than the continental lithosphere. And this is important to note now, as it will become relevant later in the chapter when we talk about the types of tectonic boundaries. Okay? So, again, oceanic crust tends to be denser because of the rock type, which is basalt. Continental crust tends to be lighter because it's mostly composed out of granitic rocks. Because the crust of either one is, or because the crust of the oceanic one is denser, the overall lithosphere in oceanic areas is denser. Because continental crust is lighter, then the overall continental lithosphere is lighter. Okay? Okay. Also, the asthenosphere is the weaker part of the upper mantle that lies right below the lithosphere, as we had seen in the previous chapter. At this depth, the temperatures are high enough and the pressures will stay low enough that rocks come close to melting. Not quite melting, but they come somewhat close to melting. So they behave in kind of the same way that clay behaves when it is compressed. It sort of moves and it flows. It doesn't bend or break like the lithosphere areas do. So again, it sort of behaves kind of like Play-Doh, a little bit denser than Play-Doh, and this is because the high temperatures and the lower pressures that exist at that specific depth. So, because of the physical differences between the asthenosphere and the lithosphere, where the former one flows when there is movement within, and the other one bends or breaks when there's movement within, these two layers move independently from one another, or rather they are in a way kind of detached in their individual movement. And so because they are independent in their individual movement, this allows for the lithosphere, which is broken up into little pieces, as we'll see later, to flow sort of freely on top of the asthenosphere, which has its own internal movement. But one kind of flows on top of the other one.